So far in the Prove It series, there's been a bit of a bias towards pure maths, so today let's show statistics some love by proving that the two different formulas for standard deviation are actually measuring the same thing. And the formulas we're talking about there are these two here. They look different because of the way the notation is arranged, but they secretly are calculating the same thing. And so that's what we're proving here today. But also, just to clarify before we begin, that we are talking about here population standard deviation, usually represented by a lowercase sigma, not to be confused with sample standard deviation, usually represented by the letter S. Not to worry if you're doing Maths A-level in England, because as of recording this video, you're only expected to know population standard deviation for that exam anyway. But just in case anybody watching this video had additional statistics knowledge, thought it was a good idea to make that clarification. But also, before we begin, I must give you the usual warning, which is... yes, we're doing this just for fun. You don't need to know this stuff for an exam. But what do you need to know in order to be able to do this proof? I'm assuming you've got knowledge of sigma notation. If you see sigma x, it means the sum of x. And x is representing a set of numbers, a data set, a list of numbers, if you will. And that can be any random set of numbers you like. Those are just the numbers we are finding the standard deviation for in this particular scenario. Now, that's something you've got to be careful of, because if you've done sequences and series content, you start to get used to the idea that whatever you see after the sigma in terms of algebra is the algebra representing the nth term of the sequence you're adding together, or I guess in this case, xth term. But it's worth noting in this case that isn't the case. X is just representing that data set rather than a sequence. So therefore, we're not allowed to use the formula half n plus 1, because that's only if you had a sequence of the numbers 1, 2, followed by 3, 4, etc., which we don't necessarily have. It's arguable, therefore, actually this notation is causing that confusion. So actually, when I get on with the proof in a few moments, I'm going to slightly change the notation to make this distinction clear so that we know we're not dealing with a sequence when we write that x there like that. I'm also expecting you to be aware that x bar is talking about mean, and therefore that's important, because if you've got a data set, you've got the numbers set in stone, then that means the mean is a particular value for that data set. So the mean is a constant value. So therefore we're going to be treating it as such in this proof here today. Also, of course, x bar, the mean, has a formula, which is the sum of all the numbers in the data set divided by the number of numbers in the data set. In other words, sigma x divided by m. And then lastly, we're going to be using the result that you can see there at the bottom, which is basically, to put it in layman's terms, this idea that if you had 2 plus 2 plus 2, a quick way of doing that would be to do 3 times by 2. If you have 2 plus 2 plus 2 n times, that'd be 2 times by n. But then if you change that number 2 to any number you like, let's call it the letter k, then that would be k times by n. So that's going to be a useful result that we're going to be using here today. Cool, we're now ready to start the proof, and we're going to start it by starting with this formula, and we're going to keep on rearranging it or manipulating it until it looks like the other formula. But as promised, we're going to start by changing the notation to make it a bit more clear that x isn't representing a sequence. So therefore, I'm going to write it as xr, because then we're talking about the data set where the first number in the data set is x1, the second number in the data set is x2, so on and so forth. As there's n bits of data in this data set we're looking at, the last bit of data in the data set is xm. So therefore that makes a bit more sense with the notation that we're now using. What we can start off by doing is by multiplying out the brackets. So if we do that, you get this if you expand those brackets fully. Because those things inside the brackets, though, are separated by plus and minus symbols, that means we can apply sigma notation to those things individually, because sigma notation just means adding stuff together, and adding can be done in either order. So therefore, we are then going to do that by making it look like this. But now, because we've split it up in that way, we can also split up the fraction into individual fractions. So therefore, that is the next step we can do. That's really nice, because now we can do some further alterations. For that sequence in the middle, we see that there is that 2x bar that's in front of the xr, and the 2 and the x bar are both constants. So therefore we can take them out the front of that mini sequence, or series I should say, and that will get us this. So that's what we've now got. That's really good news though, because now we've got sigma x divided by n appearing there, and that is just the mean. So x bar can be replaced there as well. But then we can also calculate what this comes to, because although that looks scary, this is just the sum of a constant term being added to itself repeatedly. X bar squared looks scary, but it's just a set number. So therefore, using the result we mentioned earlier, that would come to n lots of x bar squared, which is really nice because that fraction on the end can now be simplified to just x bar all squared. And that's really good news because we now have minus 2x bar squared plus x bar squared, which is just minus x bar squared. Therefore meaning, oh my goodness, that is just the other formula for standard deviation. Isn't that neat? I really like this because, as I said, all the complicated notation there makes it look like the proof is going to be something really scary, but it's actually not too many steps, and it works out in a really satisfying, neat way. So we are done. Please do consider liking the video if you enjoyed this proof, subscribing to the channel because I've got loads of these proof videos in my Prove It series. A link to another one is on the screen right now. I've also got various other extension videos you can binge watch. Please do enjoy. They're all in playlists. See you in the next video. Goodbye.